Python and many languages, there's the regular division, like 5 divided by 3, which gives you 1.666, something like that. There's another one which looks like division, but it's something else. And this one is called mod. Okay, can you tell me what mod does? It gives you the remainder after division. So, see, if you divide 5 by 3, then 3 goes only once into 5. And if you subtract, then you get a value of 2 as the remainder. And that's why you get that, okay? Now, you can rewrite this result in the following format. 5 is equal to 3 times 1 plus 2. So in general, if you do, A percent B and you got R, what that means is A is equal to B times some Q plus R. Okay, where Q is the quotient that you get when you divide, and there's some remainder. So for example, if you have like 13 candies and 3 friends try to share them, then everybody gets 4 candies each, and then what's left? It's 1, right? So you can see that the remainder is 1. So you see what Q means, right? Q is the quotient, R is the remainder. So Q is quotient. So this much is quite clear. And another thing that you can agree on is that R is always less than, the remainder should always be less than B. Do you agree? Yeah, obviously, right? If you have more than B left, so for example, you can say 13 is equal to 3 times 3 plus 4. But you don't say 4 is the remainder. Why? Because if you still have 4 candies left and 3 people are trying to share, you can still give 1 for each friend, right? And you can take 3 out of the 4 and distribute to 3 friends, and you still have 1 left. Okay, so that's a condition. Right? Now, what's a bit murky is what do you do when you're dividing a negative number? For example, what is negative 5% 3? Okay. And interestingly, if you do the same calculation in C++, this gives you a negative of 2 just because of this. Okay. But in Python, if you do negative 5% 3, you get positive 1. So, which is right? And the thing is, C++ is all about speed. And for some reason, this implementation makes it faster. That's what I think. I don't know the exact reason, but my guess is that this implementation is faster. Python is a slower language, but it tries to be more mathematically correct. And if you open any number theory book, which is a serious math book, then you would always see that the mod goes with this one. So this is not mathematically correct. This is the mathematically correct one. Okay. Now let's try to convert this into a statement like this one and see what each of these do. So this one, we know that negative 5 is 3 times negative 1 minus 2. right? 3 times negative 1 is negative 3 minus 2, it's negative 5, right? This one, we know that negative 5 is 3 times negative 2 plus 1. Right? 3 times negative 2, which is negative 6 plus 1. So it does make sense. Okay. In each of these cases, R is less than B is fine, right? Yeah. So R, the number B that we're dividing by is 3. Both negative 2 and 1 are less than 3. So it seems to be okay with this observation. But the convention that we always go with is that when you divide, regardless of whether A is positive or negative, it's always possible to choose a value of R that's between 0 and B. Here we are assuming that B is positive, okay? So we will not talk about the cases when B is negative, but even for the case when B is negative, you can take the absolute value of B to make it work, but that's not our interest. We will always divide by something positive for this one, okay? So, in other words, when we talk about remainder, we will always go with the one that fits between 0 to B. Now, I won't do the math proof here, but you can actually prove by math that if you insist on this condition for the remainder, there's always one unique remainder. Okay? There's no way to have two different remainders by writing it in two different ways. Okay? If you satisfy this inequality. And as you can see over here, this is negative, so this doesn't satisfy this condition, and this one does satisfy. Okay? So we will say negative 5, it has, when you divide by, when you mod by 3, you end up with 1. Okay. Any questions? Does this make sense? Okay, so just to make sure that we understood what's going on, let's try another negative number. See what can we do here. Say negative 23 mod 7. Okay. Well, if you, so here's the question, example 1. Well, 23 mod 7 is what? 7 times 3 is 21. That goes under 23, so what's that? 2. You get 2. Which says that 23 is equal to 7 times 3 plus 2. Now you just multiply negative to everything, so negative 23 is 7 times negative 3 minus 2. So you get a statement for this guy here, okay? Except that that's no good, right? So when we're doing A mod B, we need the remainder to be non-negative and less than B. In this case, B is 7, so we need the remainder to be between 0 and 7. We need the remainder between 0 and 7. Negative 2 doesn't work, okay? So how do I change this to make it fit between 0 to 7? Well, a simple idea is this. Add 7 and subtract 7. So by that I mean do 7 times negative 3 minus 7 plus 7 minus 2. Then this much, because this is really 7 times negative 1 plus 7 times negative, you have 7 times negative 3 plus 7 times negative 1, which is same as 7 times negative. What do you get if you do this plus this? Negative 4. And then 7 minus 2 is 5. So that's what I got. Are you following? Yeah. 7 times negative 3 minus 7 is same as 7 times negative 4. If you didn't get it, just do the calculation, see what you get. 7 times negative 3 is negative 21, minus 7, what's that? Negative 28, right? Negative 28 is clearly 7 times negative 4, right? Yeah. So this is what you get. And as you can see, this 5 does fit between 0 to 7, so that must be the remainder. Okay? So the answer here is that 5 5 is the remainder. Okay. Now, once you see that there's a way to divide negative numbers by positive numbers to get remainders, then you can talk about congruence classes. So for any number n, if modded by, or modded by 3, the remainder could be what numbers? Can you tell me all the possible remainders?
2.
2 or 1, or it could be 0 too. 0 is fine, that means it's divisible. So 0, 1, or 2. Okay. And that allows us to define the following sets. Okay? So 0 bar is actually a set where we collect every number, every integer. So this is a symbol for integers. So this is a set that has 1, 2, 3, 4, 5, 6, 7, and negative 1, negative 2, negative 3, including the 0 as well. Okay, so let's take this. Where when you mod by 3, you get the remainder 0. Now, if you write this explicitly, what belongs in this class? Can you give me a number whose remainder is 0 and you mod it by 3? 3, right? So you have 0, of course, and you have 3. What's another one? 6, 9. Okay. All of these are, these give you 0 when you mod by 3, right? And the negative ones as well. So you can have plus or minus 3, plus minus 6, plus minus 9. Then we can also define something called 1 bar. Where n mod by 3 gives you 1. Okay, if you write them explicitly, what do you get? You get 1 itself. If 1 mod 3 is just 1 because you don't get any quotient 0. So 1 is equal to 3 times 0 plus 1, right? So 1 definitely has remainder 1 when you mod by 3. What's another one?
4.
4. 4 is 3 times 1 plus 1, right? What's another one? 7. Right? And you can see that they increase by 3, right? So if you want to go to the negative side, you have to subtract by 3. So 1 minus 3 is negative 2. Negative 2 minus 3 is negative 5. Okay. All of these numbers. So for example, negative 5 is 3 times negative 2 plus 1. So it's in this set. Okay? It satisfies this equation. Right? And then 2 bar would be this one, okay? Which will give you 2, 2 plus 3 is 5, 5 plus 3 is 8, da da da. 2 minus 3 is negative 1, negative 4. Yeah. These are the numbers that's in congruence class 2. And because any number, if you divide by 3, the remainder would be one of these 3, you know that every number should belong to one of the 3 classes, okay? And there's no overlap. You can't have a single number that belongs to both sets, okay? So what this shows is that the entire set of integers can be written as union of these three congruence classes, okay? So each of these are called congruence classes. So there are three congruence classes if you mod by 3. If you mod by 4, there are 4 congruence classes. If you mod by 7, there are 7 congruence classes. That's what it means. Now, if these sets did not satisfy any mathematical properties, then we wouldn't be interested in talking about this. But it was Gauss who found some interesting properties here. So what he found was that suppose you pick the number from here and you pick the number from here. So you take 4 times 8. We multiply the two. 4 times 8. Okay? And then let's say we mod it by 3. What's that? 4 times 8 is 32. 3 goes 10 times into 32. What's the remainder? 2. But look, what's 4% 3 times 8% 3? This has remainder. What's the remainder? 1. 1. This has remainder.
2.
2. What's 1 times 2?
2.
2. Okay. So what it's saying is that if you take an element in 1 bar and another one in 2 bar, you multiply them. 1 times 2 is 2, so you get something in 2 bar. Interesting, right? Yeah. What about this one? 4 plus 8% 3. What do you get? 4 plus 8 is 12. 12 mod 3 is 0. Because 12 divided by 3 is 4 and there's no remainder. So 0. Now what's 4% 3 plus 8% 3?
3.
3. And 3 is in 0 as well, right? So what we see is that, so let me clarify what I just did as a simple rule. So if x is in 1 bar, and y is in 2 bar, then xy would be in 2 bar, and x plus y would be in 0 bar. This symbol means it's an element of, okay? And we can simply rewrite what this is saying as the following. 1 bar times 2 bar is 2 bar. 1 bar plus 2 bar is what? 3 bar, but the same as 0 bar. Yeah, 1 plus 2 is 3, but 3 is in 0, right? Yeah. So we just say that this is the same thing as that, okay? 3 itself is in the congruence class of 0, so that's what we write down. So what am I trying to say? That gives rise to something called modulo arithmetic. So we say A is congruent to B mod 3, okay? If A and B are in the same congruence class. So as an example, we can say 1 is congruent to 10 mod 3. Because what's 10 mod 3? That's 1. 1 is also, 1 also has 1 mod 3 is 1, and 10 mod 3 is also 1. Okay, we say that two things are in the same congruence class by using triple equal sign. Now there's a simpler criteria. There's an alternate definition. Alternate definition, which is to say that if A is congruent to B mod 3, if and only if A minus B is divisible by 3. In other words, A minus B percent 3 is 0. And that kind of makes sense. If A and B are both congruence class of 1, then A mod 3 will be 1, B mod 3 will be 1. So if you do A minus B mod 3, it will be 1 minus 1, which is 0, right? As you can see, obviously 1 minus 10, what's that? Negative 9. Negative 9 is self-divisible by 3. Agreed? Okay? So that's the alternative definition. So in general, A is congruent to B mod n if and only if, so this is the definition, A minus B is some multiple of n. So for some k. There's some value of k where if you multiply them it's equal to A minus B. That's just another way of saying that A minus B is divisible by n. Because of the observations that we've made before, the following is true. So if A is congruent to B and C is congruent to D mod n, okay, if that happens, then the following are true. A plus C is congruent to B plus D. Okay. And then A times C is congruent to B times D. Mod n. Now this might not sound so easy to understand, so let me show you by explicit example. Find the last digit of 3 to the 10th power. Okay. Now, if you have some number, how do you get the last digit by using mod? You just do the mod by 10, right? What's 527 mod 10? 7, right? It's 10 times 52 plus 7. So this mod just gives you 7, right? So we know that finding the last digit is same as asking for mod 10. Okay. So solution. So we're looking for x equals to 3 to the 10 mod 10. Okay. Let's see, what is 3 to the 10? That's 3 squared to the 5th power, because 2 times 5 is 10, which is 9 to the 5th power. Okay, so we can say 3 to the 10th power is congruent to 9 to the 5th power. Okay. But then 9 is 9 times 9 times 9 times 9 times 9. And 9 is congruent to negative 1 mod 10. Do you agree? Subtract the 2, what do you get? 9 minus negative 1 is 10. Right? 9 minus negative 1 is 10. Is 10 divisible by 10? Of course it is, right? So 9 and negative 1 are congruent. But what this is saying is that if you have two things that are congruent, you can replace one by the other. That's what this theorem is saying. So you can replace 9 by another number in its congruence class, which is -1, which is -1 to the 5th power. Well, -1 to the odd power is what? -1, right? Which is equal to, congruent to, 9. And because 9 is indeed between 0 to 10, 9 is indeed the remainder of, so this indeed tells you that 3 to the 10 mod 10 is going to give you 9. So without really calculating 3 to the 10th power, which is a huge number that you probably don't want to calculate, you figured out the last digit. Yeah. And this amazing arithmetic works because if you try it with the congruence classes, you see that if you work with elements from each congruence class, you can just replace one by the other and you always get the same answer. Yeah. So this is called the modulo arithmetic. And I'll show you in the next few classes how you can use this to solve interesting number theory problems. But not only that, you can use this for cybersecurity. Okay? So that part is something that I'll explain later.